So let us recall the transformation or the change of variables formula. So suppose I have a map at G from Y to R, and it is defined on some V. And an F that is a diffeomorphism C1 diffeomorphism from the set U. Since F is bijective, therefore U can be written as F inverse of V. So therefore, we can replace this by F inverse of V. So if we want to integrate over V the function G, you can integrate the composition of F and G. So that is now a map from U, which is the inverse image of V under F, into R. But now you will have this what we call a scaling factor. So this measures how the deformation from U to V via the C1 diffeomorphism F. So let us consider specific examples. The polar coordinates. In R2. So for this, let us consider the following transformation. So this is a map on this Cartesian product into R squared. So suppose let us consider the Euclidean plane, and I have a point with coordinates x, y. Then we can write this as a pair where we have r as the length and let's say phi as the angle. So this would be defined as follows. So I have an r and phi. So the x component would be r cosine phi, r, and then the y component is r sine phi. The Jacobi matrix, okay, for this function is defined is given as follows. So this is cosine phi. So that's the derivative with respect to r. And then if we take the derivative with respect to phi, that is negative r sine phi. So we took this function. Next, we take the derivative of this with respect to r, and then the derivative with respect to phi. Hence, the determinant of this Jacobi matrix is given by r cosine squared phi minus negative r sine squared phi. And the classical Pythagorean identity for the sum of the squares for cosine and sine yields that this is r. And of course, since r is positive or non-negative, we have this. Okay. However, this function is not a diffeomorphism. Nevertheless, if we restrict the domain, okay, you can check that this is a diffeomorphism from the polar from this product to r squared except 0. Okay, so take note that here, if r is 0, no matter what the value of phi, you will get the origin. So with that, this function is not a bijective. But then if we ignore or remove that point, hence removing the origin as well in R2, this one is a C1 diffeomorphism. And the good thing here is that at the set where we have removed in the Cartesian product, so that is the radius 0 at any angle, this has the Lebesgue measure 0, and in the codomain, this is a finite set, so the Lebesgue measure, two-dimensional Lebesgue measure is also 0. So applying the transformation rule, so integrating, let's say, a function g, a non-negative function or an integrable function with respect to the variables x, y, it's the same as the integral of the inverse image under the polar transformation of g. Take note that here we have these components. So this is r cosine phi, r sine phi, with respect to the variables r and phi. Well, the classical way of writing this is as a double integral. So in calculus, we wrote this as, let's say, like this. So we also have a double integral here. R cosine phi, r sine phi, and there's a missing scaling factor, which is r here. This should be d r d r phi, and therefore here you must have r dr d phi. So this is another way of looking at this. But in this course, we write what? We wrote this as a single integral. But in calculus, we use this. We write it as a double integral. Okay, so let us illustrate the change of coordinates for the polar variables. So geometrically, let's say if you want to integrate this region on the right, so think of this as this region, this wired frame, if you like. So to simplify the integration using polar coordinates, the inverse image of this region here is just a rectangle. So in this case, you can see that the radius is from 1 to 4. So here you have this radius from 1 to 4. And some angle between this and this. So for instance, if this is, let's say, this angle, so the angle in radians is around 0.25, okay, and the other angle is around 1 radians. So the inverse image of this is equal to this rectangle. So changing into polar coordinates simplifies the region of integration. So instead of integrating over this domain, we integrate over a rectangle or a cell. And from here, you can, let's say, use Fubini's theorem to write the integral over the rectangle as an iterated integral. And you can even interchange the order of integration. And here, the limits can be calculated. So geometrically, this is the significance of changing polar coordinates into, or changing Cartesian coordinates into polar coordinates. Our next example would be the cylindrical coordinates. In R3. So basically, the idea is to add one dimension in the case of polar coordinates. So here, suppose that we have a triple in the three-dimensional space XYZ. So the point XY can be written in terms of polar coordinates, where this is R, and this would be phi, and the height would be C. So in this case, our change of variables will be as follows. F sub C for the cylindrical coordinates. So similar to the polar. So this is the polar coordinates. And you take any R, okay, for the height. And this maps into R cube. So the action is the following. So I have R, phi, and Z. So you take the polar with respect to X and Y, and Z is fixed. Then as before, you can show that the determinant of the Jacobi matrix for this transformation is the same as R. Since this is fixed, so it will not contribute to any change on the Jacobi determinant. And you can show that as well. This is a C1 diffeomorphism by removing the radius 0. Hence, we can now write. So if I want to integrate this and use polar coordinates, so or cylindrical coordinates, we need to take the inverse image, then apply, okay, the transformation, and then multiply by the Jacobi determinant. In this case, it's R. So let us look at that geometrically. So think of a cylinder and cut that cylinder. So this is a portion of the cylinder where we slice it, say, from the sides and from this side. So in Cartesian coordinates in x, y, z, suppose we want to integrate over this type of domain. Using polar coordinates, you can transform this. Okay, so the inverse image of this under the polar coordinates. So here you have r, phi, and z would be a rectangle, a prism. So integrating over this prism would be easier than integrating over this portion of the cylinder. And again, you can write this as a triple integral and you may apply Fubini's theorem so that you can rearrange the variables of integration for convenience. So this is geometrically the polar or the cylindrical coordinates. So a portion of the cylinder can be transformed into a prism. So to have our final example, we consider the spherical coordinates. So for this, again, we have a point x, y, z, Cartesian coordinates. And here we will now have, let's say, this is r, this is phi. Now we have the angle from the positive z-axis to the vector determined by the point x, y, z. And let's say this is a theta. So with this, the change or the map corresponding to this change of variables is now as follows. So still the radius is from 0 to infinity. The angle is 0 to 2 pi. The angle for from the positive z-axis will now be from 0 to pi. And this is a mapping into r cube. And the change of variables would be as follows. So this is r sine theta cosine phi, r sine theta sine phi, and then r cosine theta. And you can take the Jacobi determinant, okay? But then an alternative way is to recognize that the spherical coordinates is just a composition of the cylindrical and the polar transformations. Here, the polar transformation is a bit different. So we take this as our radius and angle, and phi would be the one that is fixed. So in other words, this is r sine theta, phi is fixed, and this is r cosine theta. And you can check that this is indeed the case. And I suggest that you verify this a simple computation of decomposition. Now we apply the following. We know that the Jacobian of the composition is the following. So you take the Jacobian, then evaluate G, and then multiply it with the Jacobian of G. Likewise, the determinant of the product of two matrices is the product of the determinants. With this, we can now apply. So the determinant of the Jacobi matrix for the spherical coordinates is the product of the determinants. So here we have the Jacobian of the cylindrical at let's say rho phi z, and rho z is evaluated at r sine theta, r cosine theta. So take note, this is nothing but the polar coordinates where a phi is fixed times the determinant of the Jacobian for the polar. So we have here r phi theta. And let us take the absolute values. The first is equal to rho r. Or I should say this is equal to rho absolute value of rho times the absolute value of r. And since rho and r are positive, so this is rho r. However, we need to replace rho by r sine theta, so this is rho, or I should say r squared sine theta. Hence, with this, we can now write the formula for the spherical coordinates. And it is given by the following equation. Here we apply this function times the Jacobi determinant, which is r squared sine theta d r phi theta. And this is your familiar change of coordinates when you apply the spherical transformation. And finally, let us look at the geometrical explanation. So here you can think of this as a portion of the sphere where you cut on the sides and cut an inner sphere inside and on the other side. So from the top view, so think of this as a portion of the sphere where you cut on these sides. And this is an arc of a circle. So spherical coordinates transforms integration over such domain. In other words, such portions of a sphere again into a prism. So here you have now from x, y, z Cartesian coordinates into r, phi, theta, spherical coordinates. Again, simplifying the integration over this complicated domain into a more simple domain, which is the prism.